Hello everyone, welcome to the third lecture of the course Mathematical Aspects of Biomedical Electronics System Design. In today's lecture, we will learn about continuous time Fourier transforms, properties of Fourier transform, connection with linear time invariant systems, and Fourier transform of periodic signals. So let us begin today's lecture. We will start with defining what a Fourier transform is. Fourier transform, unlike Fourier series, applied to signals, here continuous time signals that are aperiodic. So a signal doesn't have to be periodic for us to define its Fourier transform. Fourier transform of a continuous time signal xt is defined as so this is continuous time signal its Fourier transform. We'll use x omega to denote its Fourier transform, and it's defined as minus infinity to infinity xt e raised to minus j omega t dt. Okay, let's see an example. In fact, we will see several examples. So here is our first example. Say xt is e raised to minus at ut t greater than a greater than 0. If you plot, this signal would look like follows. It's a real signal. This is 1 e raised to at minus 80. This is t. This is my xt. Okay. If we apply the above definition, we see that x omega is 0 to infinity e raised to minus at e raised to minus j omega t dt, which is 0 to infinity e raised to minus a plus j omega t dt, which in turn is minus 1 over a plus j omega e raised to minus a plus j omega t 0 infinity, and this is equal to minus 1. So we have that x omega is 1 over a plus j omega. Okay, let's see another example. Say xt is pulse signal. So xt is 1 if t is in the range minus t to capital T and 0 otherwise. If we plot this looks like following. It's minus t, t, 1. Okay. Now if we apply the above definition, we get x omega equal to minus t to t e raised to minus j omega t dt, which is 2t if omega is 0 and minus 1 over j omega e raised to minus j omega t minus t to t, which is 2 sine omega t divided by omega, and this is if omega is not equal to 0. We can compactly express this Fourier transform in terms of the so-called sinc function. Sinc function is defined as follows. Sinc of alpha is 1 if alpha is not equal to 0, and it is sine pi alpha divided by pi alpha if alpha is not equal to 0. Okay, in terms of sinc function, we see that x omega can be expressed as follows. It is 2t sinc of omega t divided by pi. If we plot this function Fourier transform, it looks like as follows. It's a symmetric function. So this is how it looks. This is omega, this is x omega. Each points are as follows. So we have 0 here. This is pi over t, 2 pi over t, 3 pi over t, and similarly we have minus pi over t, minus 2 pi over t, and so on. Okay, now let's see. Having seen Fourier transform of a signal, how can we retrieve the signal given its Fourier transform? So the inverse of Fourier transform, namely in other words, so here is the relation xt. If xt has Fourier transform x omega, then I can retrieve xt from x omega by the following operation. Xt is 1 over 2 pi minus infinity to infinity x omega e raised to j omega t d omega. Now, as in case of Fourier series, this equation is called synthesis equation. The previous equation that got xw, that is Fourier transform from the signal, that is called analysis equation. So this is called analysis equation. Let's see an example. Let x omega, this is Fourier transform of a signal, be 1 for omega be less than or mod of omega less than or equal to pi and 0 otherwise. So the Fourier transform itself is a pulse signal. This is minus pi, this is my x omega. So question is, what is the inverse Fourier transform of the signal? So xt is 1 over 2 pi minus pi 2 pi e raised to j omega t d omega. From definition, we see that if t is equal to 0 and x0 is 1 over 2 pi minus pi 2 pi d omega, which is 1, and if t is not equal to 0, then xt is 1 over 2 pi minus pi 2 pi e raised to j omega t d omega, which on simplifying becomes sine pi t. Well, first we get e raised to j pi t minus e raised to minus j pi t divided by 2j pi t, which is nothing but sine pi t divided by pi t. Okay. Which in turn, if expressed in terms of sinc function, is simply sinc t. Okay. So we have xt is equal to sinc t for all t. Okay. If you plot this xt, it looks like follows. Okay, here is the rough sketch of xt, where these points are 1, 2, 0, minus 1, minus 2, etc. Okay. So we see that the Fourier transform of sinc function is a pulse signal. Okay. Now in below we will use the following convention. If xt and capital X omega are signal Fourier transform pair, that is x omega is Fourier transform of xt and xt is inverse Fourier transform of x omega, we will denote it as follows. So Fourier, this is a signal Fourier transform pair, or sometimes also called Fourier transform inverse transform pair. Signal Fourier transform pair. So what we just observed, that for a rectangular pulse, its Fourier transform is sinc, and for a sinc function its Fourier transform is a rectangular pulse. So we see a duality between Fourier transform and inverse Fourier transform. We will see such dualities, several such dualities as we go along. So now we come to properties of Fourier transform. So the first property is called linearity. This property says that if xt has Fourier transform x omega and yt has Fourier transform, be consistent, y omega, then axt plus byt will have Fourier transform ax omega plus b omega. This property can be easily seen following the definition of Fourier transform. Okay. Here is the next property, and this property is called time and frequency shifting property. So actually these are two properties that we combine together, time and frequency shifting properties. Let's see what these properties are. It says that if xt has Fourier transform x omega, then a shifted version of xt, that is xt minus t naught, will have Fourier transform e raised to minus j omega t naught x omega. Similarly, so this is time shifting property. Similarly, if we multiply xt with e raised to j omega naught t, so this new signal e raised to j omega naught t xt will have Fourier transform, which is shifted version of the Fourier transform of xt. So the new Fourier transform is this. So we see a duality between time and frequency shifting. Okay. Let's see an example. Let us consider the first example. Recall that their xt was e raised to minus at ut, a greater than 0, and we saw that its Fourier transform is its Fourier transform was 1 over a plus j omega. Now this says that the Fourier transform of xt minus t naught, which is e raised to a t minus t naught, ut minus t naught. Fourier transform of this signal will be e raised to minus j omega t naught divided by a plus j omega. So this is an illustration of time and frequency shifting. Let's move on to the next property, which is conjugation. Conjugation property. It says that if xt has Fourier transform x omega, then x star t, which is complex conjugate of xt, will have Fourier transform x star minus omega. Okay. So in particular, if xt is real, then xt is same as x star t, its complex conjugate. This says that x omega will be same as x star minus omega. Okay. In particular, if I take modulus on both the sides, we will see that x modulus of x omega, it's also called absolute value of x omega, is same as absolute value of x star minus omega. So this is called absolute value or modulus, or sometimes it's called magnitude or amplitude. These are all same things. Similarly, angle of x omega, often also called argument of x omega, is equal to negative of argument of x minus omega. So this is called argument or angle. Right. So we see that modulus or absolute values have even symmetry, whereas angles have odd symmetry. Let's see an example of this property. Again, recall the first example that we had taken, that is xt is e raised to minus at ut a greater than 0. Recall that the Fourier transform of xt is x omega equals to 1 over a plus j omega. The absolute value of x omega in this case is 1 over root a square plus omega square, which is plotted, looks as follows. Peak value is 1 over a, so here is omega and this is modulus of x omega. Angle of x omega can also be easily seen to be minus tan inverse omega by a. If we plot this angle, it looks as follows. These values are pi by 2 and minus pi by 2 respectively. So here it's omega, this is angle of x omega. In this example, xt is a real signal, so we would expect x modulus of x omega to be real symmetric and angle of x omega to be odd symmetric, which is how they are in this pictures. Okay, so this is the conjugation property. This is an instance of the implication of conjugation property. Next property that we will see are called derivative properties. Let's say that xt is a signal that has Fourier transform x omega. If we differentiate the synthesis equation with respect to t, then we get that dxt over dt will have Fourier transform j omega x omega. Similarly, if we differentiate the analysis equation, we see that minus jt xt will have Fourier transform that is derivative of Fourier transform of xt. So this is dx omega over d omega. These are called derivative properties. We see that there is certain type of duality between these two relations. We will see in uses of this property in a while. Likewise, if we differentiate the synthesis and analysis equations k times, we get the following properties. We see that the kth derivative of xt has Fourier transform, it is j omega raised to k x omega, and the Fourier transform of minus j omega raised to k xt is kth derivative of Fourier transform of xt. We will see several uses of this derivative properties in a while, but for now we will move to the next property, that is the next we will see several uses of derivative property in a while, but for now let us move to the next property, which is time and frequency scaling. So we now move to time and frequency scaling properties. Okay, so this says that if xt has Fourier transform x omega, then xat, where a is a non-zero number, will have Fourier transform 1 over mod of a x omega by a. So here a is a non-zero number. Let's see an example. Recall that xt equals to sinc t has Fourier transform x omega, which is a pulse signal, as follows. So this is 1 between minus pi and 0 otherwise. So x omega is 1 for omega between minus pi and 0 otherwise. Now if I choose a to be equal to omega capital W by pi and consider xat, which is sinc W by pi t, then Fourier transform of this signal will be pi by W x pi by W omega, right, which in turn implies that Fourier transform of W by pi sinc W by pi t is x pi by W omega. If we see this signal, this is again a pulse signal, but between minus 1 and 1. So this is signal that takes value 1 between minus 1 and 1, and it's 0 otherwise. This is x pi by W omega. Okay. Let's now see a special uses of this time and frequency scaling properties. So this is a special case, but quite important case, and this is when a is minus 1. Then the above property implies that the Fourier transform of x minus t is x minus omega, capital X minus omega. Now we can combine this property along with conjugation properties to get some interesting fact. In particular, if x is real, if x is even, which says that xt is equal to x minus t, then x minus omega is same as x omega. This follows from the above equation. If xt is, moreover, if xt is real, that is xt is equal to x conjugate t, conjugate xt, then the conjugation property says that x minus omega is equal to x star omega, that is conjugate of x conjugate omega. We combine these two properties, then we infer that if xt is real and even and real, then x omega is same as x star omega. In other words, x omega is real. We have already seen several illustrations of this example. For instance, let us recall the two examples that we saw earlier. In one, xt was a pulse signal. So this was our first example. The other one was where xt was sinc function. In both these examples, xt were real, and so as expected, x omega, xt was real and even, so as expected, x omega also turned out to be real in both the cases. X omega are real both the cases. Let's now move to the next property, which is called Parseval's relation. This relation is as follows: minus infinity to infinity mod of xt square dt. This can be expressed in terms of integral of mod of x, absolute value of x omega squared, and integrated. So this relation is called Parseval's relation. Let's see an example that illustrates this. We again go back to the example where xt is e raised to minus at ut, a is greater than 0. In this case, we have readily seen that x omega is 1 plus j omega. Let us compute the following integral: minus infinity to infinity xt square dt, which in this case becomes 0 to infinity e power minus 2at dt, which on simplification gives 1 over 2a. On the other hand, if I compute the following: minus infinity to infinity x omega mod square d omega, this is minus infinity to infinity 1 over a square omega square d omega. This turns out to be pi over omega, or 2 pi over 2 omega. This last equality implies that 1 over 2 pi minus infinity to infinity norm x omega square d omega is equal to minus infinity to infinity xt square dt, as claimed by Parseval's relation. So this is an illustration of Parseval's relation. Next we will see a few corollaries of this properties that we have already seen. Namely, we see that the initial value of the signal in time domain can be, that is x0, can be obtained as 1 over 2 pi minus infinity to infinity x omega d omega. This relation is obtained by simply setting t equals to 0 in the synthesis equation. Similarly, if I set omega equal to 0 in the analysis equation, I get the DC component of the signal. Namely, I get capital X0 to be equal to minus infinity to infinity xt dt. See the right hand side, it's akin to average of the time domain signal. Okay. Next property is multiplication property. It says that if xt has Fourier transform, say x1t has Fourier transform x1 omega and x2t has Fourier transform x2 omega, then product of the two time domain signals, that is x1t times x2t, will have Fourier transform which will be 1 over 2 pi times convolution of x1 omega and x2 omega, that is x1 star x2 omega. If we expand this, we get 1 over 2 pi minus infinity to infinity x1 omega x1 theta, say x2 omega minus theta d theta. So this is Fourier transform of product of two time domain signals. The dual of this result is what is called convolution property, a very important property. We will see many uses of this. So convolution property, it says that if x1t has Fourier transform x1 omega and x2t has Fourier transform x2 omega, then convolution of x1 and x2, that is x1 star x2t, this will have Fourier transform that will be simply the product of x1 omega and x2 omega. Let's see an example illustrating this property. Recall that if I set xt to be equal to pulse signal, that is 1 if mod of t is less than or equal to 0.5 and 0 otherwise, pictorially here is my xt, say minus 0.5, 0.51 t, so xt, then the Fourier transform of xt, x omega, will be given by sinc omega over 2 pi. This is obtained by simply setting capital T equals to 0.5 in the example that we had seen earlier. Now in this case, the convolution of x with itself, that is x star xt, turns out to be a triangular pulse. Namely, it is this function, and the above convolution property states that the Fourier transform of this pulse is sinc omega over 2 pi whole square. Okay, so this way we get Fourier transform of a triangular pulse from Fourier transform of a rectangular pulse. Okay, let's now see a few uses of convolution property. As I indicated earlier, this property has many uses. And the first use is in computation of convolution of functions. So, see, convolution of, suppose I have two signals x1t and x2t, I can use this property to compute x1 star x2t. Not always, but in several interesting problems. So here is an example. Let's say x1t is e raised to minus at ut and x2t is e raised to minus bt ut. Here a, b are both positive and a and b are unequal, they are not same. Okay, we readily know that the Fourier transforms x1 omega and x2 omega are respectively a plus j omega and 1 over b plus j omega. Okay, in this case the product of the two Fourier transforms is 1 divided by a plus j omega times b plus j omega. We know that the inverse of this Fourier transform, inverse of this product, would give convolution of x1t and x2t. So let's try to find out the inverse of this. Towards this, we will use the technique of partial fraction expansion, which says that we can write this right hand side as a by a plus j omega plus b by b plus j omega for two numbers a and b. This can further be worked out to be ab plus ba plus ja plus b divided by a plus j omega times b plus j omega. If we equate the constants and multipliers of omega, then we get that, we see that AB plus BA is 1, whereas A plus B is equal to 0. On simplifying, this gives A to be equal to 1 over B minus A, which is same as minus capital B. So we see that x1 omega x2 omega is equal to 1 over B minus A, 1 over A plus j omega minus 1 over B minus A, 1 over B plus j omega. We readily know that the Fourier transform of this signal, inverse Fourier transform of this signal is e minus at ut, and for this function its inverse Fourier transform is e minus bt ut. This says that inverse Fourier transform of x1 omega x2 omega is 1 over b minus a e minus raised to minus at e raised to minus bt ut, right? And from the above property, this is equal to convolution of x1 star and x1 and x2. So we see how convolution property allows us to compute convolution of two functions. Let's see another example. I again take xt to be e raised to minus at ut, where a is positive. Now I am interested in convolution of x with itself. We see that we cannot use the partial fraction expansion property used above. However, I can use convolution property along with derivative property to compute this convolution. To see that, observe that x star xt will have Fourier transform which is x omega whole square, which we know that 1 over a plus j omega square. Okay, notice that this 1 over a plus j omega square can be written as j times d over d omega 1 over 1 plus j omega. We can compute the derivative and can verify this assertion. Right? So this in turn is equal to d over d omega x omega. Right? We know that d over d omega x omega has inverse Fourier transform which is minus jt xt. So this has inverse Fourier transform minus jt xt. This says that this whole thing j d over d omega x omega will have inverse Fourier transform which will be minus j square t xt. This says that convolution of x with itself is nothing but txt. Notice that minus j square is 1. Okay, which in this case is t e raised to minus at ut. So we see how we could use these properties to get convolution of x with itself. In fact, we can repeat this process k times to get k times convolution of xt, and the result turns out to be as follows. So Fourier transform k times convolution of x with itself, t turns out to be equal to e raised to k divided by factorial k e raised to minus at ut. So we see that this is quite useful property. Okay. Now we will see uses of this properties in analyzing LTI systems. So we will see connections to LTI systems. Recall that in an LTI system whose impulse response is ht, if we give input xt, the output yt is convolution of xt and ht. It is convolution of xt and ht. So from the convolution property mentioned above, we know that Fourier transform of yt, that is y omega, will simply be x omega times h omega, right? Where h omega is given by, where h omega is Fourier transform of ht. So that is h omega is minus infinity to infinity ht e raised to minus j omega t dt. If we recall the first lecture, this is what we defined as frequency response of the system. So we see that frequency response of the system is nothing but Fourier transform of impulse response. Let us now use the relation that we have just derived to get frequency response of continuous time LTI systems. Frequency response of continuous time LTI systems. Recall that systems are characterized by following differential equation: k equals to 0 to n ak dkyt over dtk is equal to k equals to 0 to m bk dkxt divided by dtk. If we use derivative property, we can write a Fourier transform of both the sides as follows: k equals to 0 to n ak omega j omega raised to k equal to k equals to 0 to m bk j omega raised to k, which in turn implies that from the definition of frequency response, h omega equals to y omega j omega raised to k x y omega equal to k equals to 0 to m bk j omega raised to k x omega, which from the definition of frequency response further implies that frequency response h omega is y omega divided by x omega, which in turn is equal to k equals to 0 to m bk j omega raised to k divided by k equals to 0 to n ak j omega raised to k. Okay. Let's see an application of it. So an example. Consider the following system called first order, which is a first order system. Given by differential equation tau dy over dt plus y equals to xt. Okay. Tau here is often referred to as time constant. If we compute the Fourier transform of both the sides using derivative property, we see that j omega tau y omega plus y omega is equal to x omega, which in turn gives the frequency response h omega as y omega divided by x omega to be 1 over 1 plus j omega tau. Okay. Notice that the modulus or the absolute value of this function h omega is 1 over root 1 plus omega square tau square, which if we plot looks as follows. Okay. So this is absolute value of h omega. The peak value is 1, and at omega equals to 1 over tau, the value is 1 over root 2. So this value 1 over tau has special significance. Okay. In fact, we can compute the inverse Fourier transform of h omega to get impulse response of the system, which turns out to be 1 over tau e raised to minus t over tau ut. Here we have used scaling property of Fourier transform and an earlier result on Fourier transform of such functions. Okay. So this was an example of Fourier transform to LTI systems. Let us now take a step back and look at the definition of Fourier transform. Notice that, recall that Fourier transform for a signal xt was defined as follows: minus infinity to infinity xt e raised to minus j omega t dt. Okay. This very definition raises a few questions. For instance, does this integral, when does this integral exist? Are there any sufficient condition for existence of this integral? What happens for xt for which this integral does not exist? So let us try to answer a few of these questions. First, we will state a result that ensures existence of this integral. Okay. So here is a theorem that says that if minus infinity to infinity mod of xt dt is finite, then this integral exists. Okay. Not only it exists, x omega is continuous, and moreover it approaches 0 as omega goes to infinity or minus infinity. So x omega approaches 0 as omega approaches plus minus infinity. However, notice that this is a sufficient condition. As we will see soon, it's not a necessary condition for existence of Fourier transform in the sense discussed here. So this is sufficient but not necessary. Let us revisit a few of the examples that we saw earlier. clarify this point. One of the examples has xt to be equal to pulse signal minus t to t. Let's call this signal xtt. Okay, so this is xtt. Clearly this is absolutely, so this notion of this in the left hand side, this is called absolute integrability. Absolute integrability. So absolute integrability is enough to ensure existence of Fourier transform. So this xtt is absolutely integral. So its Fourier transform is guaranteed to exist. The same goes for the signal, let's say this triangular signal. Recall this signal, which was convolution of two rectangular pulses. This is also absolutely integral. Well, that also absolutely integral. So above theorem implies existence of Fourier transform for these. So absolute. Right? This is absolute. Implies existence of Fourier transform of these signals. On the other hand, if we see the sinc if we consider the sinc function where xt was equal to sinc t, this is not absolutely integrable. I will not get into details of why it's not absolutely integrable, but it's important to notice that even though it's not absolutely integrable, its Fourier transform exists. That is, the integration that defines Fourier transform is well defined. But minus infinity to infinity xt e raised to minus j omega t dt is well defined. But what about the signals for which this integral, Fourier transform integral, is not well defined? Let's see, for instance, xt equals to 1 for all t. So this is a constant signal. Okay. For this signal, this integral minus infinity to infinity e raised to minus j omega t dt is not well defined. The same holds for xt equals to, okay, so the same holds for xt equals to sinusoidal signal, that is, the same holds for xt equals to say cos omega t. So what do we do in these cases? It turns out that in this case we can appeal to a generalized, more generalized notion of Fourier transform, and that is what I'll explain now via an example. Okay, so let us consider. So this is what we are going to see, is a generalized notion of Fourier transform that doesn't necessarily require the Fourier transform integral to exist. Generalized notion of Fourier transform. Let us recall the signal xtt just mentioned above. So xtt is minus t to t. It's 1 and it's 0 everywhere else. Recall that its Fourier transform is 2t sinc tw by t omega by pi. Okay, let's call this xt of omega. I am writing subscript capital T just to show the dependence on capital T. Okay. Now as t goes to infinity, as t goes to infinity, this xtt converges to the constant function. Why? Its period becomes longer and longer, so it converges to constant function. Where so we would expect that the Fourier transform of the constant function will be given by limit t tends to infinity capital x capital T omega. Okay, now let's see what this right hand side is. Okay. So this x capital T omega has a couple of interesting properties. First property says that if I integrate it, x t omega d omega minus infinity to infinity, I know from the initial value property that 1 over 2 pi times this is x0 which xt0 which is 1. So one of the properties of minus infinity to infinity xt omega is that this is equal to 2 pi. Let us call this property star and observe another quite interesting property of xt omega, which is following. If I compute limit t tends to infinity xt omega, then this turns out to be limit t tends to infinity 2t, which is infinity if omega is equal to 0, and this is limit t tends to infinity 2 sine omega t by omega if omega is not equal to 0. Now if I plot this function xt omega for larger and larger values of capital T, I see the following, I observe the following. Suppose for some t I have the following plot. If I increase t, the amplitude at omega equals to 0 increases, and at the same time the plot gets compressed. So I see something of the following sort. We can imagine that this picture along with these two properties, namely star and double star, will imply that as we increase t to infinity, this xt omega converges to Dirac delta function. More precisely, it converges to 2 pi delta omega. See, 2 pi here coming from the fact that integral of xt omega over omega is equal to 2 pi for all values of capital T. That gives rise to this 2 pi delta omega. So from the above we can conclude that this constant function has Fourier transform 2 pi delta omega. Even though the above argument looks a little complicated, the same can be verified from the following observation. If we use synthesis equation for Dirac delta function, then we see that for x omega equals to 2 pi delta omega, xt is 1 over 2 pi minus infinity to infinity 2 pi delta omega e power j omega t dt, which is nothing but 2 pi get cancelled, so it is 1. Okay, so we can follow the similar logic to get dual results as follows. So the dual to the above pair is if xt is Dirac delta function, then its Fourier transform is 1 for all its constant function for all omega. Again, this can be justified with analysis equation, which says that for xt equals to delta t, analysis equation implies that x omega will be minus infinity to infinity delta t e power minus j omega t dt, which is 1. Okay. Now we can use frequency shift property to derive a generalization of the above relation. Shift. If we do a frequency shift to get xt equals to e j omega naught t, then its Fourier transform turns out to be x omega equals to 2 pi delta omega minus omega naught. Okay, so this is a more general result. Now let's see a few of the implications of this result, few of the uses of this result. Until now we have seen Fourier transform for aperiodic signals, but what if we are faced with periodic signals? Fourier transform of periodic signals. Let's say we have a periodic signal xt for which we can write the Fourier series. So xt is minus k equals to minus infinity to infinity ak e power jk omega naught t. We can then use linearity along with the above property to write the Fourier transform of xt to be equal to k equals to minus infinity to infinity 2 pi ak del omega minus k omega naught. Let's see an example. If xt is cos omega naught t, then xt can be written as half e j omega naught t plus half e power minus j omega naught t, and accordingly the Fourier transform of xt can be written as pi delta omega minus omega naught plus pi delta omega plus omega naught. Let's see another example. Suppose xt is an impulse stream, that is k equals to minus infinity to infinity del t minus kt. Okay. In this case, we can compute the Fourier series coefficients of xt as follows. So xt h ak is 1 over t minus t by 2 to t by 2 del t e minus j k omega naught t dt, which is 1 by t for all k. Right? So now I can write the Fourier transform of xt x omega as follows. It is k equals to minus infinity to infinity 2 pi by t, okay, del omega minus k omega naught. Notice that 2 pi by t is constant, so I can bring it out of the summation, and Fourier transform can also be written as follows. So this brings us to the end of our discussion of Fourier transform for continuous time signals. Next lecture we will look at Fourier transform for discrete time signals.